Okay, so here's the example for the categorical variables. So let's talk about a chemical process, a coal cleansing system. So Y is the dependent variable which shows the amount of suspended solids in the system. Okay? And X is the pH of the system. And you can use three different polymer types, okay? 1, 2, and 3. Hence, since there are three polymer types, I will have two indicator variables, Z1 and Z2, okay? And since I have one continuous variable, one independent variable, that's X, I just write Xi. It's not X1i because I have a single variable, okay? Well, the model takes the form beta 0 plus beta 1 xi, beta 2 z1i, and beta 3 z2i. Right? Well, the model is this, where if z1 is 1 and z2 is 0, it means that you are just using polymer 1. If that's 0 and the second one is 1, it means you are using polymer 2. If both of them are 0, then you are just using polymer 3. So here is the data. Okay, you have 18 experiments, right? So for example, so let's assume you're just writing this into a text file or into an Excel sheet. Then you have Y here, so this is Y, right? This is X, and we will have also Z1 and Z2, right? So this is using polymer 1, which means you will just write 1, 1, 1, 1, 1, 1 here. And this is 0, 0, 0, 0, 0, okay? 1, 0. And the second one, it uses polymer 2, which means you have 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1 here, okay? And the next one is you have 0, 0, 0, 0, 0, 0, 0, 0. Sorry, 0, 0. Okay, that's 0 as well. So that's how you just encode each independent variables for a particular observation. Okay, so this is the first observation. This is its y value, and these are the x and z values of that particular observation. Okay, so what we will do is we will just write this into the Excel. Okay, so this is, let's say, column A, column B, column C, and this is column D, right? And then say Excel that, well, just make the regression using Y and these X's, right? These are my X, these are my independent variables. Or again, you will just put them into the text file for the R and just read it from this file where the X's are 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, and these ones. Okay. Of course, at the very beginning, you always have 1, 1, 1, 1, dot, dot, dot. That's for x0. Okay, that's for beta 0. Okay. So it turns out that, well, so let's look at this. So this is my intercept minus 161,900. So this is my model. Y is equal to minus 1,601.90 plus beta 1, which is this one, okay, 54.29 times x1, right? Plus z1, which is 90 times z1, and the second one is plus 27.17 z2. So what does this mean? What does this mean? For example, if you just want to find a prediction, for example, for this one, okay? So its real value, it's yi, let me just call this is y4. Its y4 is 378. I want to find y4 hat. Y4 hat is equal to simply, so it's a polymer 1, 8.4, 8.4. So that's equal to y hat 4 minus 161.90 plus 54.29. What is x1? I forgot it. That's 8.4. 8.4 plus 90 times z1. What is z1? It's 1, right? And 27.17 times what? Z2 is 0. Okay, just look at here. Z2 is 0 and Z1 is 1. So if you just plug in the values, okay, if you just plug in the values, so let me just calculate this. So I just calculate this. So it turns out that this is equal to 384.136. Okay, so this is the this is y4 hat. This is the estimate for the fourth observation, and its real value is 378, right? 378. And okay, so this is what we have found. It turns out that the p-values are all positive, so that's fine. They can stay in the model. Later, we will see how to just include and or extract the variables from the models. But for now, it seems that all are significant. And one last thing is that, well, what are the meanings of 90 and 27? So just consider this. What is 90? That's the estimate for B2, right? That's the estimate for B2. So if Z1, okay, if Z1 is equal to 1, then what you do is you just add 90, okay? Just look at this one. Or let me just go back. Okay, just look at this one. So it turns out that the estimate for this one is 90, right? That come here. And the other one is 27.7p. And this is 27.7p. So what does beta 1 mean? So what does beta 2 means? If this is 1, right? If this is 1, then you just add beta 2 to the mean response, okay? If it is 0, then you don't add anything. But beta 2 is added if Z1 is equal to 1, right? So what does this mean? So just look at this one. All of them are 0, and only Z1 is equal to 1. So the difference between these two things is what the difference is beta 2 which is equal to 90. So what does 90 mean? 90 means the difference between polymer 3 and polymer 1. So polymer 1 has an so it's let's say what was the so y was the amount of suspended solids. So the amount of suspended solids in polymer 1 is greater than polymer 3 by 90, okay? And how about B3? That's equal to 27.17. Let me change my color. So beta 3, 27.17 is added whenever Z2 is equal to 1. Okay, so just look at here. So Z2 is equal to 1 here, and all of them are 0 here. Okay, so the difference between these two is what? This is equal to beta 3, which is equal to 27.17. What does this mean? The difference between these two is equal to 27.17, which means the difference between, so again, just look at the definition of Y, the amount of suspended solids in the system due to polymer 2 is greater than polymer 3 by an amount of 27.17, okay? So beta 1, beta 2, sorry, beta 2 and beta 3 shows the additional value added to the variable y due to using polymer 2 or polymer 1 instead of polymer 3. So here the basis where all of the z values are equal to 0. So the basis polymer 3, beta 2 shows the difference between polymer 3 and polymer 1, and beta 3 shows the difference between polymer 3 and polymer 2. Okay, so you may, if you just change the encoding, so you may just say, for example, I'm just making it up. If you just say, for example, Z1 is equal to 0 and Z2 is equal to 0, that's polymer 1, okay, polymer 1. Z1 is equal to 1, Z2 is equal to 0, that's polymer 2. Then Z1, 0, Z2 equal to 1, that's polymer 3, okay, polymer 3. Then beta 3, okay, no, but yes, Z2 for beta 3. So beta 3 shows the difference between polymer 1 and polymer 3, okay? So what will be the value of this one? So the difference between polymer 1 and polymer 3 is, we know from the previous, it's 90, but it's the additional value of polymer 1 over polymer 3, right? Now we are talking about the additional value of adding additional value of polymer 3 over polymer 1, which will be minus 90, okay? So beta 3 in this example, beta 3 will be equal to minus 90. And how about beta 2? Okay, how about beta 2? It will show the difference between the first and the second polymer, okay? So do we know the difference between the first and the second polymer? Well, we do not, but we can just extract from the values of 90 and 27, right? So it turns out that the basement is polymer 3, which is, let's say this is 0. If you just add polymer 2, you will have 27.17, okay? So this is what this is polymer, sorry. This is polymer 3, and if you just add polymer 2, then you will have an additional value of 27. And if you just add polymer 1 to over polymer 3, you will have 90, which is, if you just, let me just put it like this, and the difference here with the 90, that's equal to, let's say, almost 62.83, okay? So from polymer 3 to polymer 2, you have 27.17, right? Which was beta 3. So this is what? This is beta. Is it beta 3, right? And from polymer 3 to polymer 1, this is beta 2. And between polymer 1 and polymer 2, the difference is 62.83. Okay, so this is the difference between polymer 1 and polymer 2 in favor of polymer 1. So just look at here now. Well, here I have beta 2. It's the difference between polymer 1 and polymer 2, which is 62.83. But here I'm just looking at the additional value of polymer 2 over polymer 1, which should be again negative. This is equal to minus 62.83. Okay, so this is how we deal with the coefficients of the categorical variables. Right? Okay, and this is what we have. Okay, this is what we have. Just look at this one. So here the intercept will be at minus 600 and 162 minus 135, and the difference here is minus 72. Okay, so just look at here. The difference here is, so the difference here is what? 27, right? The difference here is what? 63, right? And the difference here is what? 90. Okay, that's exactly what we did when we are trying to understand the values of beta there, right? So polymer 3 has the lowest intercept. Polymer 2 is just over it. It's parallel to polymer 3, and polymer 1 is just above all of the lines, above two polymers. Again, it's parallel to the two lines, so their slope are the same: 54.3, 54.3, and 54.3. The difference is at their slopes. Okay? So all of the variables, the pH level and the polymer type, turns out to have impact on the resulting Y, right? Because we have all of the p-values. So all of the p-values here turns out to be what they're significant. So the most effective polymer is polymer 1 because, as you see, well, its regression line is just over all of them. Okay, so for any given pH value, it just gives you the greatest value of Y. Okay, so it produces the highest amount of suspended solids, which means you have high Y values. Okay, high values. And the least effective one, of course, polymer 3. Well, so here we talk about the parallel slopes, but there may be some examples where you have non-parallel slopes. Okay, so there may be some interaction between the categorical variable and the continuous variable. So just consider a model with one continuous variable and indicator variable with two categorical variables, right? So just look at this one. I have a model. This is an independent variable x, and this is a categorical variable. So it is either 0 or 1, which means we have two categories. But the thing is that, well, this category is what? This category is also interacts with what? With x, right? So this is, again, it's not a nonlinear model because it's linear in terms of the parameters. And what you have is that if z is equal to 0, right? If z is equal to 0, you have something like this, beta 0 plus beta 1x, right? Z is 0, this one cancels, this one cancels. If z is equal to 1, then you have something like this. Beta 0 plus, now this is beta 2, right? So you have something like this as the intercept plus z is equal to 1. And so you have beta 1 plus beta 3, okay? Plus beta 3x, okay? Great. So you have different intercept and you have different slope, okay? Okay, this is a regression. This is for Z1, different intercept with this one, and this is different slope for this particular thing, right? So the slope here is beta 1, this in this one, okay, in this line. The slope in this line is beta 1. The slope in this line is beta 1 plus beta 3, okay? The intercept here is beta 0, and the intercept here is beta 0 plus beta 2. Okay? So just think about an example regarding this. So for example, if you are talking about the price of a car, so for example, let's think the price of a Mercedes, okay? So let's say the price of a Mercedes, and if you just try to make a regression with the price of Mercedes versus its kilometer, and the price of a, for example, let's say Shaheen, again, with respect to the kilometer. So what you expect to see is that, well, the amount of the car which just reduces by kilometer is different in Shaheen and Mercedes. Okay, so each kilometer just reduces the value of the car, but this amount is high in Mercedes. Okay, but it's low in Shaheen. So you will have something like this. Mercedes just starts at a very high value and just goes down more steep. So Shaheen starts here, okay, and its value just goes down. Again, goes down by the kilometer, but it just goes down. Let's say more, also less steeper than Mercedes.